Apologies in advance. I'm obviously a little bit iller than I thought I was, so I am sniffing at various points throughout this video, something I've just noticed after editing everything together.
To uh, the YouTube channel I use for maths videos, and it'll be useful to get feedback at some point about whether it's more useful that way or it's more useful for classrooms, because it's certainly much more useful, easier for me to upload it to YouTube than it is classrooms. Sometimes there's a file limit issues, which means I kind of have to downgrade the quality a little bit, but yeah, let me know on classrooms whether this was easier or more difficult. Right, so there will be timestamps for each one, which again I think is part of what should hopefully make this a bit easier. You should know how timestamps work on YouTube. So there'll be a timestamp for sort of unit 1, 2, 3, 4 and 5. So as you may know, this exam is going to be kind of mainly on content that was learnt in the spring term, but there will be content on unit 1 and unit 2, which was rounding and estimating and solving equations. And then units 3, 4 and 5, which we should have learned this term, are, well, of course you may have started on unit 6 as well, but the exam will only be on to unit 5, will be sequences, plotting linear equations, and percentages and proportion. Okay, so without further ado, here we go.
So, this number here, which is so big, I can't even, 34,895,894, there you go, rounded to the nearest 100,000. Okay, so first of all I need to identify where the 100,000s column is. Let's start with that. I know that's the thousands columns, that's the tens of thousands there, so this is going to be the hundreds of thousands column, that one right there. Okay, so I'm going to round to the 8. So I look at the next number, is it 5 or bigger? Well, yes it is, which means that this is going to get upgraded to 3, 4, 9. Okay, but after my rounding point, I do need to fill in a bunch of zeros. I've got 1, 2, 3, 4, 5 zeros to fill in for obvious reasons. If I don't put in those zeros, then my number is going to be vastly different to what I started with. So there we go. We've got 3,490,000. No, I don't know. It's that. It's definitely that. That's your answer. Okay. Right, let's have a little look at decimal places. So it's kind of the same skill really. We find the first decimal place here, which is the 5. I put my little rounding point next. I'm going to cut everything off after that. Now the next number, is it 5 or bigger? No. So I can just leave that as 14.5. Easy peasy. Right, next question is rounded to 2 decimal places. It's basically the same thing, but obviously the second decimal place is here, so I'm going to put my cut-off point there. Another change, of course, is that the next number is 5 or bigger, so I'm going to change this to 0.45 before cutting everything off. 0.45. Right, and then we get this example here. This is quite a popular, kind of slightly tricky question. I call it a chain reaction. You'll see what I mean in a minute. So if we round to 2 decimal places, my cut-off point is here. Okay, if I look at the next number, is it 5 or bigger? Yes. So it's going to round up that 9, but then that's going to round that 9 up, which is going to round that 9 up. Now, another way I like to think of it is like, well, we're going from 19.99 to 20.00. We're kind of ticking up by 1. But yeah, either way you think of it, we're going to end up with 20.00 because of that chain reaction. Again, another way you might want to think about it is, think about it as 1,999. If I went 1 up from that, what have I got? 2,000. But then, of course, remember you need to put your decimal place back where it should be before. And you can leave your answer as 20.00 or 20. I like to leave it as that, just to kind of show any examiner that I have recognised it's been rounded to 2 decimal places. But of course, 20.00 and 20, they're one and the same thing. Right, significant figures. Okay, so I purposely put decimal in here. The most common mistake is to think, right, is that the same as decimal places? No. When we're thinking about decimal places, we're actually counting from the left. Sorry. When we're thinking about significant figures, we're actually counting from the left. So the first significant figure is the 4. Okay, significant means important. So the most important figure in that number is the 4. It's worth 1,000. Whereas the thing 400, 10, so on and so forth. So the second most important figure, and therefore the second significant figure, is the 7. So that's where our rounding point's going to go, right there. So again, we look at the next number. Is it 5 or bigger? Yes. So that 47 becomes 48. Well, it's not really 48, but that's the way I think of it when I'm rounding. And then obviously I need to pop a couple of zeros in, otherwise we're changing our number, our whole number, to something much smaller. So 4,800 is our answer there. Right, 0.00345. So the funny thing about significant figures is we don't start counting until we've had our first non-zero digit. So actually that's the first significant figure, and this right here is our second significant figure. Okay, so looking at cut-off points, the cut-off point after the second significant figure goes there. Obviously my 34 goes up to 35, and we make sure that we've included all the zeros that were there before. I'm going to redo that because that's a little bit knotted together. There we go, there's our answer. Okay, and then this one here is a tricky one. Remember I said you don't start counting until you've had a non-zero number. A common mistake is to think, well, that's a 0, so we don't count that. Once we've started counting, we don't stop. So we start here, this counts as the first, this counts as the second, even though it's a 0, because we've started counting, and this counts as our third significant figure. So 0.07069, I'm just going to rewrite that out. Our 6 is our third significant figure, so cut-off point goes there. So 0.0706 becomes 707, because of course the next number is 5 or bigger, and that's our answer. Right, error intervals. I often like to look at these on a bit of a number line. So 450 has been rounded to the nearest 10. I've actually worded this quite poorly. I would normally say a number has been rounded to 450 to the nearest 10. What is the maximum that number could have been? Okay, so we've got this mystery number, we don't know what it is, but it was rounded to 450. Now if we count up in tens, the next number after 450 would be 460, and the number before would be 440. Okay, now this number must be somewhere in between halfway to 440 and halfway to 460. If it were any further, we'd round it down to 440, wouldn't we? And if it were any higher up there, we'd round it up to 460. So it's got to be in between those two. So the highest that number can be exactly halfway in between 450 and 460, which would be 455. Okay, but we've got another problem. Actually, if we had 455, that would round up to 460. So you might say, okay, well, the number before that, 454. Okay, that's not going to round up to 460, and that's pretty high. But we could say, well, you could go higher than that. You could go to 454.9, 454.99, and forever and ever and ever. So actually, kind of officially the highest you can get is 454.99, just before that halfway point. But look, to make things a bit less complicated, I would write my answer as x is level. I've got my crocodile the wrong way around. X is going to be less than 455. So you've got two possible answers here. Okay, it's just before the halfway point is the highest you can go. You either write that the maximum is 454.9 recurring, or use inequality terminology like I've done up here, say x has got to go up to but not include 455. Okay, so to one decimal place, similar thinking here, we're actually going to find the maximum and the minimum. So counting up in one decimal places, the number that comes after 4.5 is 4.6. And the number that comes before is 4.4. Now we're looking for the lowest and highest we could be at and still round to 4.5. So we're looking at our halfway points. So the halfway point between 4.5 and 4.6 is 4.55. So that's the highest we can go up to. And the halfway point between 4.4 and 4.5 is 4.45. So that's the lowest we can go down to. Remember, if we go any lower, we're going to round to 4.4, so that's too far. If we go any higher than 4.55, we're going to go to 4.6, so that's too high. So these are our maximum and minimum points. Now, as I said before, we can use inequality terminology here, and this is what's known as an error interval. So if we actually say x is strictly less than 4.55, but on the other side, I'm going to do a slight, what I call the greater than or equal to, it's the less fussy crocodile, I call it, because of course we can go up to 4.45 because it would still round up, okay, because 5 always rounds up. So we don't have the same inequality on both sides. So you can either draw that as an inequality, or you can say, look, the minimum it can be is 4.45, the maximum it can be, remember, we can't go up to 4.55, so we've got to say 4.549 recurring, which can be a bit of a pain to do, but that's the highest we can go without being 4.55. Okay, I personally, and in maths, we generally work with this when we're doing our calculations, but this is fine as well. Okay, just to make it a little bit more tricky, significant figures, but actually it's not really that much tricky. You know it's been rounded to 7.93. You know the third significant figure is there. That means it's basically the same as it's been rounded to 2 decimal places. So if we count up to 2 decimal places, the next number after 7.93 will be 7.94. The number below 7.93 will be 7.92. So again, looking at our halfway points between the two, I can write this as an error interval. So 7.935 is our halfway point, isn't it, between these two? Notice it always goes 1 decimal place beyond what you've had it rounded to. 7.925 is our halfway point there. So x has got to be in between 7.935 and 7.925. Again, if you want to write that as min, you can say the minimum it could be is 7.925, but if you're going to write just the max, remember we can't actually go up to 7.935, so we've got to go 9.349 recurring. Yeah, that's that. Right, now notice the question's changed slightly. We do need to state the error interval, so you've got no choice. The good news is that in a maths exam, when they asked you specifically for an error interval, they'll actually set the error interval up for you, ready to go. And I'll be honest, if this was included in any exam I make for you, the error interval will be set up ready to go. So that's all right, you don't have to remember which way around the crocodiles go, that's there for you. It's been rounded to the nearest hole, so we count up in holes. The halfway point between 13 and 14 is 13.5. Remember, we go beyond there, we'd be too low, we'd round down to 13, so that's our lower end. The halfway point between 14 and 15 is 14.5, and there we go. Right, estimation. Okay, so sometimes in life you've got to do a calculation quickly, and you don't want to get your phone out of your pocket, I don't know, or you just want to give a value that's not full of decimal points and all sorts of numbers. So we round it to something that's going to be a bit easier. Now you actually have a choice. Like, I could round this to 3,100 times 4, or maybe I could round it to 3,000 times 4, or maybe if you're extra quick at doing stuff in your head, you could round it to 3,103 times 4. But the first rule you have to adhere to here is you must round in your calculation. You will get 0 marks if you just do the calculation as it is, and it will take you ages to do, and you might get it wrong anyway. So even if you get it right, you get 0 marks. You must round at least one value before you do your calculations. The other rule of thumb I say to myself is, if you can't do it in your head in 5 seconds, you've not rounded easily enough. I'm going to be honest with you guys, this is probably about as far as I could round in 5 seconds, and I'm stalling here while I try and do it in my head. That's 12,300. Okay? But there's nothing wrong with doing the easier calculation. 3,000 times 4, 12,000. That will be considered just as valid in an exam as that, albeit this one's slightly more accurate. If it makes you feel good, fine, but it's a lot of extra effort for, yeah, this one here, 12,300, and you can see the problem here. I'm struggling to do this in my head. 12,312, I think, is the answer. I wouldn't bother rounding to that. You're not getting extra marks for it. The examiner doesn't care about how clever you are at calculating things in your head. Pick one that's easy to do that you can do in 5 seconds. Okay, this is interesting because we used to, when we round, right, my first instinct there would be to go, right, so I've got to do 53 divided by 9.4. My first instinct would be to go, well, okay, so let's do 50 divided by 9. Of course, we have a problem here. 50 divided by 9, that's not something you can do in your head in 5 seconds. Okay, so we've made a calculation that's too hard. Look, the rules for estimating, you don't have to round to the nearest 10 or whole number or whatever. You can round to what's convenient. So actually, it would be more convenient to round that to 54 divided by 9, because 54 is in the 9 times table, and the estimate that you do will be more accurate because you've only moved your number by 1 rather than moving it by 3 to make 50. So actually, you can make it easier on yourself and have a more accurate estimation. So 54 divided by 9 gives me 6. If I were to do 50 divided by 9, by the way, and I'm quietly pulling out my calculator here, I'd like to claim I'm doing it in my head, I get 5.5555555, and the real answer to the question, by the way, 53 divided by 9.444 is 5.6. So, you know, it might have been more accurate doing it this way. On this occasion, it seems to be. Is that really? I feel like I must have written something down wrong there. Oh, that's divided by 0.44. Oh, okay. 5.554. You know, I don't know what's going on there because this should be more accurate, but honestly it doesn't matter. This would be accepted as correct, and that's much easier to do. Now, with regards to, you can be asked in GCSEs, is this an overestimate or an underestimate? So, is the answer you've given less than or more than the real thing? Well, we can see the real thing here is 5.6. Okay? You do have to explain why though. Okay, why it's an overestimate. Why you know it's an overestimate. You can't say, oh, I calculated it on my calculation, it was. You have to kind of do it this way and say, look, well, what I did, right, was the real sum was 53 divided by 9.4. What I actually did was 54 divided by 9. So essentially, right, I increased what my actual number is, and I decreased what I'm dividing by. Well, if you increase what you've got, and you share it with a smaller number, overall, your answer is going to increase, isn't it? So this is an overestimate because I increased my number and I reduced what I'm dividing by. It's an overestimate. That's my answer there, and that's my reasoning. Right, similar to before, again, if I tried to do the square root of and said, oh, let's round that to 50, you can't do the square root of 50 in your head. It doesn't go. But you don't have to round it to the nearest 10. I could do the square root of 49, and now not only is my answer going to be more accurate because I've only moved my number 2 rather than 3, but I can do the square root of 49 because it goes quite nicely. It's 7. Okay, so especially with square rooting, you're not necessarily going to stick to the rules of rounding to the nearest 10, 100 or 1,000. Right, quite common to get a functional question, and for good reason, to be honest. This is an area of maths you're most likely to use no matter what job you end up taking. We're all going to end up doing some kind of DIY or building of something or buying of some stuff for a party, and you kind of want to quickly get an idea of the costs. So, Selena is painting her bedroom wall. Her walls have an area of 154. Each paint pot can cover 43 metres squared. So in order to work out how many paint pots I need, first of all, I'm going to need to do 154 divided by 43. For obvious reasons, I don't want to do that. But if I round this to 160 over 40, I can do that within 5 seconds in my head. That's about 4 paint pots. Okay? Right, 13.79. Again, I don't want to do that. I don't want to do 4 times £13.79. So again, I'm going to say, well, let's round that to £14 instead for a cost of about £56. A rule of thumb really for real life as well is whatever you estimate it to, just have a little bit more cash than that in your pocket in case your estimate's wrong. I'd bring £60 along to the store if I thought it was going to cost 56. I say that, nobody really carries cash anymore, it's contactless, isn't it? But I'm waffling. Right, equations. I'm sorry for this analogy, but it's true, and I'm always saying it in my classes. This is Mr. Miyagi, and this is the Karate Kid, the original one, played by Ralph Macchio. There's a series going on at the moment called Cobra Kai, which I strongly suggest watching. It's very good, but again, I digress. So they have this argument at the beginning where he wants to learn karate, he wants to learn how to fight, how to do the complex stuff, and he's just teaching him to go wax on, wax off, paint left, paint right. I can't remember what that second thing is. He's bored of learning these simple steps. He wants to learn real karate. And then at the end, he actually gets him to put those simple steps together, and he finds that he's able to fight incredibly well. And I think that actually applies to equations here. There are times in class where people say, look, I've got my own method for doing this, I can just see it in my head, I don't want to learn these simple steps. And then it gets complicated and people get lost. So if we focus on always following these simple steps, even if you think you don't need to and it's a waste of time, when it gets more complex, you aren't going to have to think, it's just going to be mechanical memory, you just do it and you can solve more complex equations than if you started by just trying to do it all in your head. So case in point, right, 5x equals 20. So 5 times a mystery number is 20. Well, you know your times tables. You know that it's going to, 5 times 4 is 20. So I can just say x equals 4, move on to the next one. No. Wax on, wax off, we're going to do the step. So, there's a word here, coefficient. I use it in my classes. Coefficient is the posh word for the number in front of the variable. So the x coefficient here is 5. So we always divide by the x coefficient to finish our equation or to solve our equation. So, because our x coefficient is 5, we're going to solve our equation by dividing by 5. Okay, and the reason we do that is if we divide by the coefficient, it cancels it out to 1. So we end up with x equals 20 divided by 5, 4. X equals 4. Again, you're thinking, well, I don't need to do that. Okay, but let's come to the next one. 3x equals 7. Well, 7 isn't in the 3 times table, so you're stuck, aren't you? Well, wax on, wax off, we always know we divide by the x coefficient to solve our equation. So x 3x divided by 3 becomes a normal x. 7 divided by 3, good news, can't do it, so you can leave your answer as 7 divided by 3. As a decimal, if you had a calculator, the answer would be 2.3 recurring, right? But you aren't going to have a calculator, and you might make a mistake trying to convert to a decimal, so just leave it. If it doesn't go, just leave it as 7 divided by 3. Now, on this occasion here, our x coefficient is actually divide by 5. So to get rid of divide by 5, we need to do the opposite of divide by 5, which is to times by 5. But we must keep balance in everything we do with equations. So if we times x over 5 by 5, we must times 25 by 5. So those two will cancel out. X equals 25 times 5, which is 125. Okay, and that should make sense. Look at it, it's saying a mystery number divided by 5 is 25. Well, 125 divided by 5 makes 25. It's tempting to think the answer to this might be 5, because you see 25 and you see 5. That's done on purpose to try and trick you sometimes, but no, it's 125, and if we follow our rules, we'll always get to the correct answer. Okay, let's move on to a negative with one step. Things don't change just because there's a negative. Wax on, wax off, we always divide by the export. coefficient. It just happens to be minus 4 this time. But minus 4 will cancel out minus 4, and now you've got to do 32 divided by minus 4. Well, 32 divided by 4 is 8, so 32 divided by minus 4 is minus 8. So even when the negatives come along, sticking to that method, we get our answer. Okay, let's move on to two-step equations. Okay, so our first step is get rid of the number that is with your variable. So we want to get rid of plus 7, so we minus 7 from both sides. We've now got 2x equals 4. Okay, so there's an obvious reason why there's a two-step equation. Step number 2, 2x equals 4. And again, you're thinking, come on, I know 2 times 2 is 4. I know the answer is 2. But, of course, we come across to this next question here, and it's not always that nice. So I add the 7 to both sides. That cancels out the minus 7. I've now got 3x equals 25. As you see, 25 is not in the 3 times table. But if we stick with our method, wax on, wax off, we divide by 3, we know that's going to solve the equation. 25 divided by 3. And again, 25 divided by 3 doesn't go, so we can just leave it as 25 over 3. That's perfectly fine and acceptable. Right, this one here doesn't seem like a two-step equation, and lots of people would tell me the answer to this is 10. You see 14, you see 4, difference between 14 and 4 is 10, there's a minus going on in there, that must be the answer. But it's not. And let's follow our steps. First of all, this is a plus 4, not a minus 4. The minus belongs to the x. So our minus 4 from both sides, minus 4 from both sides, that cancels that out. We've now got minus x equals 10. Okay, but we're not looking for what minus x is, we want to know what x is. And bear in mind, this is actually minus 1 there, not... We never mention the ones, but they're always there when x is on its own. So our x coefficient is minus 1. So to solve this equation, wax on, wax off, we're dividing by minus 1. And I promise that's the last time I say wax on, wax off to you. I'm sure it's getting a little bit boring now. So x actually equals minus 10. How does x equals minus 10? Remember, 4 minus a mystery number equals 14. Well, if that mystery number is minus 10, then we'll have 4 minus minus 10, which actually becomes a plus. So 4 plus 10 makes 14. So yeah, x equals minus 10 is the answer. And if we follow our steps, you're not going to make that mistake. Okay, so last one here. We've got a minus 8 from both sides. Be careful, that's a plus 8 there. The minus belongs to the minus 4x. Minus 8 from both sides. I've now got minus 4x equals 9. And I divide by minus 4. Divide by minus 4. Okay? We'll always cancel out the x coefficient. So we've now got x equals 9 divided by minus 4. Now, a general habit here, move the minus to the top. It doesn't actually matter whether the minus is on the top or bottom of the fraction. So x equals minus 9 over 4. 9 over minus 4 would be accepted, but you know, it's etiquette. It's like not having your elbows on the table. We always put our minuses to the top of the fraction. Right, equations with variables on both sides. You're not seeing double. I'm going to solve this equation twice, just to show you that it doesn't matter what your first step is. So, we want to get rid of a number here. Now, I like to get rid of the negative number first of all. So I'm going to add 3 to both sides, and that's going to get rid of that minus 3. We've now got 7x equals 4x plus 21. Okay? Now, we want to get rid of a letter. Now, we could get rid of the 7x, but if we did that, we'd end up with nothing on that side. Okay, if I minus 7x from that side, minus 7x from that side, I'm going to have 0 equals minus 3x plus 21. We can recover from that, but it's not ideal. So generally what we do is we always get rid of the x that's got a number next to it. So, hang on a sec, let's grab that out. And let's do this the nicer way. I'm going to minus 4x from both sides. okay, which leaves me with 3x on that side. It cancels out the 4x, 3 equals 21, okay. Then we obviously do our final step, I'm not going to say it, x equals 7. Okay, so we've gone from 2 steps to 3 steps. Sort out the numbers, sort out the x's, then do your dividing or multiplying step. Now what if I'd done it the other way? What if I'd decided to minus 18 from both sides? Okay, so that now cancels out the 18 and I've got 4x. And now I've got 7x minus 3. You can see why I like to get rid of the negatives rather than get rid of the positives, because I've now got to do minus 3 minus 18, which is minus 21, by the way. Okay, this now means I've got to get rid of 7x. Get rid of 7x on both sides. I've now got minus 21 equals minus 3x. Okay? And then it's still the same step. I divide both sides by minus 3. That will get rid of the x coefficient. Minus 21 divided by minus 3 is 7. 7 equals x. X equals 7. They're the same thing. But you can see, obviously, I've had to deal in negatives. And I don't particularly enjoy dealing with negatives. I don't suppose most of you do either. Okay, so for this one, it seems just like the rest. So I'm going to get rid of the negative. Okay, so I'm going to get rid of that minus 8. We've now got 6x, obviously those cancel out, equals 11x plus 26. Okay, but as you can see, we can't avoid a negative here. I can't get rid of 6x because it leaves me with nothing and it's extra steps. So I have to get rid of the minus 11x. So I'm afraid sometimes you cannot avoid negatives, especially if one side is bigger than, well, one side it's got more stuff on it, shall we say. So that's going to leave us with minus 5x equals 26. But again, we're still finishing up the same way. We divide by the x coefficient. Wax on, wax off. Sorry, I couldn't resist. X equals 26 over minus 5. And again, we can leave it like that. If some of you are feeling a little bit posh, you could always turn it into a mixed number. But just remember that we leave our positive at the top. Right, I think I've got one last question for you. Oh, apparently I've got two last questions for you. We'll see. Right, so yeah, if you've got brackets involved, it's actually not more difficult. You've just got an extra thing to do at the top. Remember from year 7, you need to expand that bracket out before you do anything else. So 5 times 2x becomes 10x, 5 times 5 becomes 25, and obviously that equals 7x. Notice something a bit strange here. We've got an x on its own on that side. We've never had that before, but it doesn't really change what you've got to do here. You've got to make sure you've got a number on one side and an x on the other side. We can't take away 7x because we'll end up with nothing. So we minus 10x instead, okay, which obviously cancels out that 10x, and we've now got 25 equals minus 3x. And again, we always divide by the x coefficient. So my answer is that x is going to be 25 over minus 3. And remember, let's have good etiquette here. Let's leave the 25 on top. Okay, final one. Notice most of these aren't whole numbers. I'm afraid that's the way it goes with higher GCSEs, of which we're all going to be having a go at them one day. They quite often give you questions that give you fractional answers in the GCSE. So we'll get used to that now. Right, so let's expand this out. I've got to do that and that. So 9 times 2x gives me 18x minus 45 and 3x plus 7. Okay? Right, so we're ready to go just like we were before. Step number 1, get rid of a number. I'm going to get rid of the 45 because I don't like negatives. So I've now got 18x equals 3x plus 52. Now I've got to get rid of 3x. Now I've got to get rid of 3x. 15x equals 52. And I've got to divide by the x coefficient, always my final step, as we've been doing all along. 52 over 15, and we can leave it at that. Sometimes if you can simplify the fraction, do. Just so happens that none of the fractions I've given you did simplify on this.
Right, so what is the term-to-term rule of the following sequence? Right, term-to-term rule, not something we need to overcomplicate. Basically, what do you mathematically have to do to get from one term to the next? Okay, every number in a sequence is given a term number. So the first number in the sequence, term 1, is 7. The second term in the sequence is 10. The third term is 13. Okay, my term-to-term rule, as in what do I have to do to get from one term to the next, is simply plus 3. Okay, so now I know the term-to-term rule is plus 3. I know the next term will be 16, and the next term after that will be 19. Okay, if you are asked the term-to-term rule, do not overcomplicate it. Okay, I'll talk about that later, but there's another similar question that's more difficult that people sometimes confuse this with. But term-to-term rule, what do you have to do mathematically to get from one term to the next? Okay, so what's the term-to-term rule for this sequence here? As you can see, we're no longer adding, actually we need to multiply to get from one term to the next. So in this case, I'm going to need to times by 3. And I've given myself a bit of a difficult task here because I've not got my calculator on me and I need to do 81 times 3. I think that I can do. That should give me 243, but it's 243 times 3 I'm slightly worried about. That's going to be 729. Okay, there we go. That's it. So term-to-term rule times by 3. Next two terms, 243, 729. Right, so what's the next term in this sequence? Slightly more complicated here. You're not being asked the term-to-term rule. The term-to-term rule may be a little bit annoying to explain. So we just ask you what's the next term in this sequence. So as you can see, we added 3 here. Then we added 4. Then we've added 5. Okay, so hopefully you've seen the pattern here. We're essentially adding 1 more on than we did the term before. So we're going to add 7 to get to the next term, which is going to take us to 30 to get to the next term after. Oh, actually, we only have to do the next term, so that will do. Right, this is a special type of sequence known as the Fibonacci sequence. So the special name we give to a sequence like this is the Fibonacci. You're not going to be judged on if you spell it 100% correct, but that is how it's spelled, the Fibonacci sequence. Right, so the way this Fibonacci sequence works is you add the two numbers before to get the next one. So 3 plus 4 gives us 7, 4 plus 7 gives us 11, 7 plus 11 gives us 18, and if we want the next term in the sequence, we're going to need to do 11 plus 18, which is going to give us 29. And then if we want the next term in the sequence, we need to do 18 plus 29, which is 47, I believe. Okay, and that's it. So that's Fibonacci sequence. Watch out for that. Right, this is just a definition thing here, really. You're very unlikely to be asked a question on this, but you should know the difference between an arithmetic sequence and a geometric sequence. So we've actually already covered this. As posh as their names are, an arithmetic sequence is just one where you add on the same amount to get from one term to the next. Okay? So if there's a consistent amount you add on or take away to get from one term to the next, we've got an arithmetic sequence. So if we plussed or minused 2 all the time, it would be arithmetic. In this case, we're plussing 2 each time, so we've got arithmetic. A geometric sequence is when there's a multiplier in between each term. So if we decide to say, instead of add 2, we times by 2 each time, then we're going to get 2, 4, 8, 16, 32, and so on. As you can see, there's a consistent amount we times by. There isn't a consistent amount we add, because it's 2, then 4, then it's 8. So there's no consistency there. It's not arithmetic, but it is geometric. Okay, right. Position to term rule of a sequence is, how do I explain this best? It is a rule that takes us from the term number, the position in the sequence, to what the actual term is. So with our first sequence, its position is 1. Okay, so it's position, and we want to go to the term, so its actual value. Okay, so we've been given a rule here. We take the position, times it by 3 and add 7, and that gives us the actual term, position to term rule. So if I take 1, times it by 3 and add 7, that's going to give me 10. Okay, if I take 2, times it by 3, I'm thinking ahead there, times it by 3 I'm going to get 6, add 7, that's going to give me 13. Okay, if I've got 3, I'm going to times it by 3. If I've got the third position to term in the sequence, 3 times 3 is 9, 9 plus 7 is 16. And you will have noticed a pattern by this point, so you no longer need to just go through that whole rule. I can see it's clearly meaning I'm adding on 3 each time. Done. Right, so slightly more difficult. What is the position to term rule of this sequence? So this is the first of the questions where I'm going to give you an alternate version afterwards so that you can practice. Okay, it's important to practice for the more difficult questions. The questions where you're more likely to make mistakes, practicing helps you remember. So if you see that I've done an extra version of the question along my revision, I've done it because I think this is important and the kind of thing people commonly make mistakes on. Okay, so what's the position to term rule of this sequence? So first of all, let's write down the position. I'm actually only going to go with 4 because I'll get the pattern with only 4 of them. So the first term is 5, the second term is 9, second term is 13, the next term is 17. So we've got to come up with a rule, times by something, times or divide, but I will only give you times, plus or minus something gets us to our actual term. Okay, luckily for us, well, obviously we'd have to do a lot of trial and error, but luckily for us there's a big clue, right? If you actually look at the term to term rule, that actually tells you what you need to times by. So since the term to term rule is that there's a difference of 4 each time, that actually gives us the clue that our rule starts with times by 4. Okay, so what we're going to do here is we're going to create an intermediate sequence where we just do the first step. So we've worked out the first step is just to times the position number by 4. So 1 times 4, 4. 2 times 4, 8. 3 times 4, 12. 4 times 4, 16. Okay, and what you'll notice is that there's a really close link between the multiplication part of it and what we actually end up with. As you can see, the sequence we're looking to end up with is always 1 more. So clearly what we need to do is times by 4 and add 1. And that's our position to term rule. Times by 4, add 1. Okay, so step 1, look at the difference between the terms in your sequence. That tells you what you're going to times by. Create a sequence by timesing the positions by that amount, and then look at the difference between what you've got by doing that and what you still need to do. Okay, so by timesing by 4 we got to here. We still need to add 1 to make it work, so that's our rule. Okay, so this next one's for you to do. You may want to pause the video and have a go at this one yourself. Okay, so as before, let's look at the difference between the terms. As we can see, it's going up in 3s. Okay, so let's create our intermediate sequence by timesing by 3. First part of the rule. So 3, 6, 9, 12. Okay, so we look at, right, what do we still need to, so we times by 3 and that's what we ended up with. What do we still need to do every time to make this work? We clearly need to minus 1 each time. So our rule and our answer is times by 3 minus 1. Right, nth term is actually very similar to position to term rule. The only difference is that it's sort of given to you in an algebraic format. Okay, so 7n minus 2 is basically saying you take the position number times by 7 and minus 2. That's what it means. Okay, so the first number in my sequence, let's start with that. Our position to term rule is times by 7 minus 2. So the position number, by the way, is represented by n. So if you're wondering how this is the same, 7n is the same as 7 times n, which is the same as n times 7, and minus 2. So the position number, instead of me like saying position number, it's just represented by the letter n and simplified into an algebraic formula. Okay, right, so we need to take the position number, times it by 7 and minus 2. So 1 times 7 is 7, minus 2 is 5. 2 times 7 is 14, minus 2 is 12. 3 times 7 is 21, minus 2 is 19. And you should notice that it's going up in sevens. You may have worked this out already. When we were reversing it, we could see that what you go up in is what you multiply by in your rule. Okay, we're supposed to be doing the first 5, so let's do one more. I know I'm adding 7 each time, so that's going to be 33. Okay, right. The major part of this that you are more likely to be asked exam questions about, both in GCSE and, if I'm honest, in the main end of term exam, I'm more likely to ask about this because of how it links to the GCSE. Position to term rule is something we learn in year 8 when we're just sort of getting used to the language and the terminology. Okay, but when it comes down to it, the wording that's going to be used in your final GCSE exam is going to be, what is the nth term rule for the sequence? So that's what really you should be focusing on. So 2, 5, 11, 14, what is the nth term rule for the sequence? Okay, so as before, let's use our position to term method that we did before. So 2, 5, 8, 11. Remember, we don't need to go through all the terms we've got because we'll get the pattern quite quickly. Right, position, the first, second, third and fourth term. Okay, remember, we first look at the difference. Okay, so it's going up in threes. Okay, so we know the first part of our rule is we need to times by 3. Okay, let's now create that intermediate sequence by timesing the position number by 3. So 3, 6, 9, 12. Okay, as you can see, this is the same question we've done earlier, by the way. I'm just going to take you how we translate this into nth term. Okay, so what do we still need to do to get to our actual sequence? We times by 3, and as you can see, we're always 1 above, so we need to minus 1. So our position to term rule is minus 1. Okay, now some teachers will actually get you to write, and I know I do, 3n at this point, and we'll come back to that later. But anyway, so our position number we times by 3 and minus 1. Remember, with nth term we use n to represent our position, so it's n times 3 minus 1. If we're turning this into algebra, a proper algebraic expression, this needs to be turned into 3n, so 3n minus 1. As you can see, the usefulness of saying, right, I know this is the 3n bit of it, is that I can say, well then we minus 1 from 3n, so you can get straight to there. Okay, it's up to you whether you decide to go from the position to term rule, convert that position to term to n, convert it to a proper expression. Yeah, up to you. Right, you can then be asked, okay, now you know the nth term rule. What's the 100th term in the sequence? And this is the whole point of nth term rules. Like, why do we need an algebraic formula to go from the position to what we've actually got? Well, in reality, sequences are often very long, and if we're looking for something 100 terms in the future, we don't want to count through 100 terms. We want to jump immediately there. So we want the 100th term in the sequence without having to do everything in between, and that's what this rule is useful. So we already know we've got 3n minus 1. We already know we need to do 3 times 100 minus 1. So 300 minus 1, 299 is our answer to that part. Okay, have a go at this one yourself, please. Pause the video. Okay, so like before, 7, 9, 11, 13, 15. Okay, let's investigate that. So we're going up in 2s. Okay, so we already know that the first step of our position to term is we're timesing by 2, which gives us 2, 4, 6, 8. Okay, so I've just realised that I've really badly lined that up, and that's going to create confusion. So let's just reverse slightly. 1, 2, 3, 4, and we can forget about 15, we don't need it. Right, hopefully that looks a bit better. So our first step is to times by 2, 2, 4, 6, 8. They were times the position number by 2. And what do we always still need to do to get to our final answer? We need to add 5. Okay, so our position to term rule is times by 2, add 5. Therefore our nth term rule is n times 2 plus 5, or 2n plus 5. You have to leave it like that, otherwise that's not going to be accepted. Right, we then use that rule for the 100th term in the sequence, so we just need to do 2 times 100 plus 5, nice and easy there, 205. Okay, I can't remember if I've given you an extra one to... Yes, I have. Okay, so this is practically the same, but there's a little bit of a twist. This sequence is going down. Okay, so we still follow the same steps. We write this sequence out: 18, 14, 10, 6, and we'll stop there. Okay, so 1, 2, 3, 4. Now when we look at the difference, we are minusing 4 each time. Minusing 4 each time. Okay, so when we do our multiplication stage, we're not timesing by 4, we're timesing by minus 4. Okay, we need a sequence that's going down. Okay, so 1 times minus 4 is minus 4. 2 times minus 4 is minus 8. We've basically got the minus 4 times table. Okay. Now, this is where this one can be a little bit difficult. If you look at this and say, right, what do I need to do to get this to match up? At first glance, it looks like what we've got doesn't work at all. Minus 4 and 18, minus 8 and 14. What's the difference between them? Well, if you want to find the difference, like there will be a consistent difference. So if you want to find the difference between any two numbers, you need to subtract them from each other. You may look at that straight away and see 22. I do, but you know, I've been teaching maths for a long time. So I need to times by minus 4 and add 22 to get from 1 to 18. I need to add 22 to get from minus 4 to 18. If you don't see it that way, you can subtract minus 4 from 18. That's how you find the difference between any two numbers, and you end up with that double negative. Okay, and you'll see that that rule still works. So to get from minus 8 to 14, I need to add on 8 to get to 0, and then another 14 to get to 14. That's still adding 22. Okay, to get from minus 12 to 10, that's still adding 22. Okay, so my term to term rule is I times by minus 4 and then I add 22. That's how we've started up at 18 and we're actually going down in force, because we've added 22 and then we're taking 4 off, and we're taking 4 more off every time from 22. Anyway, to convert this algebraically then, we need to do n times minus 4 plus 22, so it's minus 4n plus 22. Okay, so pause the video and have a go before I do the answer to this one. Okay, so 35, 30, 25, 20, 1, 2, 3, 4. As you can see, we're going down in fives. So our rule is going to be times by -5. So -5, -10, -15, -20. Okay, what do we need to add or subtract from -5 to get to 35? I see it straight away, it's 40. But if you don't, do 35 minus -5, and that will give you 40 as well. Okay, so our sequence is -5 and then add 40, which is -5n plus 40. Okay, this is just a little bit of a challenge one for those who want to prepare for a slightly more challenging version, I suppose. I will pause so you can have a go. Okay, so still the same method. 1.7, 2.6, 3.5, 4.4. Okay, what's the common difference between them? We're actually going up 0.9 each time. Okay, which means our rule is to times by 0.9, which, you know, we can do. It's just like times it by 9. 1 times 0.9 is 0.9. 2 times 0.9, instead of 18, it's 1.8. 3 times 0.9, 2.7. 4 times 0.9, 3.6. So if you know, well, I mean, you've got a calculator, but you could do this in your head. If you know your 9 times tables, you know your 0.9 times tables. Okay, what is the difference between what we've got multiplying and what we still need to do? Hopefully you notice, but remember, you can always take the first term from the first term to get the difference. We've got a difference of 0.8. So our formula is 0.9n plus 0.8. Still all works with decimals as well. Okay, so for the following sequence, is 342 in the sequence? Okay, so we'll actually need to solve this algebraically. So what we're going to do, right, we've got a formula for the position in the sequence, and it's supposed to equal 342. So if we get the right value of n, we're supposed to get 342. Okay, so let's solve this as an equation. We've done equations. If we minus 5 from both sides, we've now got 7n equals 300 and, struggling for a moment there, 337. Okay, right, and if we want to solve to find out what n must be, we need to divide both sides by 7. Remember, you've got a calculator for this exam. Okay, and we get n equals 48.1. Well, what does that tell us? It tells us it's not in the sequence. Okay, remember, the sequences have to be whole numbers. We have the first, we have the second, we have the third, the fourth, the fifth, so on and so forth. In order, so then we'll have the 48th term, 49th term, so on and so forth. In order for 48.1 to be in the sequence, it would have to be in between two numbers. It's in between the 48th term and the 49th term, which means it's not there. So if you solve for n and you don't get a whole number, it's not in the sequence. Okay, so have a go at this one yourself, please. Pause the video. Okay, so is 356 in the sequence? Let's solve for n and see what we get. So 3n plus 11. Take away 11 from both sides. We end up with 345 equals 3n. Okay. Remember, you've got a calculator for this. So we get 115 equals n when we divide both sides by 3. Okay, so it means it is in the sequence because we've got a whole number. It's the 115th term in the sequence. Okay, what is the first sequence that's going to be larger than 300? Okay, so we solve again. 4n plus 7 equals 300. What is the first term in the 4n plus 7 that's going to be larger than 300? So if we take 7 from both sides, we've now got 4n equals 293. Like, we can already see n's not going to be in the sequence, but don't worry about it. So we divide both sides by 4, and we get, I just need to use my calculator there, n equals 73.25. Now look, that's fine, 300's not in the sequence. It will be in between sequence 73 and 74. Okay, but we're being asked, what is the first term to be larger than 300? So we know if we go for the 74th term in the sequence, we know it's going to be larger than 300. It's going to be the first term larger than 300, and it will be in the sequence. So yes, you'll get a decimal, but actually if you just go up to the next whole number, you'll get the first term larger than that. Okay, so that's the end of the sequences unit. Okay, so in this example, we need to fill in the missing coordinates and write a rule that connects the two. So on this occasion, where we've got a few coordinates already, we can fill in any that fit on the graph. So minus 2, 0 goes here. It doesn't go there, goes there. Minus what? Oh, this isn't a good start, is it? That is not the correct coordinate. Let's try again. Minus 2 minus 1 goes here. Minus 1, 0 goes here. And we've got one more coordinate. We don't really need it, but just for accuracy, 1, 2 goes up here. Right, once we've got those three coordinates that we've already been given, we can draw a line between them, which I'm not going to do the full line because it's easier on my pad just to do it from there. Obviously, ordinarily, you'd want the full line to go all the way. Oh, well, I've done it now. Okay, and I can use that to fill in the missing coordinates. So when x is 0, we can see, when x is 0, we can see that y is 1. When x is 2, we can see that y is 3. Right, write a rule that connects the two. You'll be better at this looking at it later. But what you should notice is that whatever the x coordinate is, the y coordinate seems to be one more than that. Okay, so to get the y coordinate, the rule is simply to add 1. Okay, next key learning point, create a table of values yourself from scratch and plot the graph. So I'm going to create the table of values for y equals 2x minus 3. I can use what values I want, and I usually use positive values because it's easier, but I'll throw in some negative values. So minus 2, minus 1, 0, 1, 2, and y is going to be whatever x is doubled minus 3. My rule is y equals 2 times x, then minus 3. Okay, so when x is 2, double 2 is 4, 4 minus 3 is 1. When x is 1, I do 1 times 2, which is 2, minus 3 gives me minus 1. When x is 0, 0 times 2 is 0, minus 3 gives me minus 3. And hopefully at this point, you'll realise that as we go sort of backwards down the coordinates, going down by 1 each time, the y value goes down by 2. You may notice this, but actually what's going on here is it's got a gradient of 2. That's why there's a change in y of each coordinate. Right, I can use any coordinates I like here. I'm going to use minus 2, minus 7 because that actually, and I'm also going to use 2, 1 because that actually makes my graph a lot easier to draw because they're a little bit further apart. So I'm going to my line mode. That's not line mode. Let's try again. We go to line mode. There we go. And join those two together. Obviously in the real thing, you'll have a ruler, so that'll be much easier to do. Or at least I hope you'll have a ruler. Right, for y equals a third x minus 2, in principle we start off with the same thing. We're going to do a table of coordinates. However, our rule is that whatever x is, we've got to times it by a third and then minus 2, which is much more difficult to do. So we want to pick values that will be times by a third really easily. So if I pick 0, 3 and 6, which are all multiples of 3, then I'll be able to easily times them by a third. So 0 times a third is still 0, minus 2 gives me minus 2. 3 times a third is 1, minus 2, 1 minus 2, sorry. I might actually visually show you that one. So 3 times a third is 1, and then minus 2, that gives me a result of minus 1. And 6 times a third is 2, minus 2, that actually gives me 0. Okay, now I've got 3 coordinates. I can pick any 2 I need to draw this, but let's put them all in here. So 0 minus 2 is here. 3 minus 1 is here. And I actually see that 6, 0 doesn't even fit on my graph, so I can't even use that one. But it's okay because I've got 2 points. So I'll join those 2 together and I've got my line. Okay, as you can see, as you may already know from the back end of this subject, you can see the gradient is a third. Okay, right, key learning point number 4, we need to find the gradient of all of the following lines. So the rule for the gradient is the change in y divided by the change in x between any 2 points will give you the gradient of the whole line, because of course any 2 points are on that line. So I'm going to pick 2 points that are as close together as possible sometimes, but for now let's just start with these 2 at random. This one here and this one here. I've picked these 2 because they're on the actual crosshairs, so I can read off those coordinates and I can see the exact distance between them, and I draw a right angle triangle between those 2 points. Okay, that's got a rise of 4 and a run of 2. So into my change in y divided by change in x, I'm going to do 4 divided by 2, which is 2. So the gradient of that line is 2. Right, this next one here, if I pick these 2 points here, okay, I actually see that I've got a negative gradient. Now, how do I know this is a negative gradient instead of a positive one? It's because from left to right, which is of course how we read and how we generally do mathematics, it's going downwards. So this is a negative gradient. So the change in y is minus 3, the change in x is 1, giving us a gradient of minus 3. In theory, you could read it from right to left. If you read it from right to left, if we took this coordinate and this coordinate here, technically speaking, going from right to left, we'd be going backwards by 1 and up by 3. And then we'd have 3 divided by minus 1, which still gives minus 3. But hey, if that's confusing you, don't think about that too much. Right, as you can see with this one, the gradient's not as clear, so we have to be really careful which points we pick. I'm going to pick this point here because that meets a coordinate properly, and the next one I can see that meets a coordinate properly is here. The other one is down here, but it's much easier to count the squares if I go from here to here. So I can actually see what's going on here is between any 2 points that we can easily read, there's a change of 4 in y and a change of 3 in x. So the gradient is actually 4/3. That doesn't simplify. So yeah, that's actually the gradient for that one. It's just 4/3. Okay. Key learning point number 5. We need to draw a line with a gradient of 3 and a y-intercept of minus 2. It's easiest to start from the y-intercept, which in this case is minus 2. Remember, the y-intercept is where it crosses the y-line. Okay, so it crosses the y-line at minus 2. So I know my graph, my line at some point is going through that point. I've got a gradient of 3, which means for every one along, I'm going up by 3. So my next point's there. As I said in class, you don't actually have to draw those lines. I just do it sometimes because visually it's easy to show, but you might just count in your head 1 along, 3 up, pop the next one. We don't need 3 points, but as I've said before, sometimes you'll draw 3 points so that you've got a more accurate line. You are not going to be marked down if like your line is, you know, just slightly off, as long as it's obvious where your line is meant to be. I mean, if you look at my line here, I've slightly missed that point there, I wouldn't mark myself down for that. Nobody would mark you down for that. As long as it's obvious what you were trying to do and you're only just missing the points, you're all right. This is not an art or graphics exam, so you're not going to be judged on slightly having wonky lines. Okay, so this one we've got a slightly more difficult issue because the gradient's minus a third. Well, let's start with the easy bit. Let's start with the easy bit, and the y-intercept is 5. Okay, so I know my graph's going through there at some point. Now, a gradient of minus 3 over 1, bear in mind that gradient is rise over run. Technically speaking, it means for a change in y of minus 1, we have a change in x of 3. You might think, well, hang on, why weren't we doing that when the gradient was 3? Well, we sort of were. 3 is the same as a gradient of 3 over 1. Mathematically, because 3 over 1 is the same as 3, that's how we write a final gradient when it's a whole number. But it's always in the back of our mind that for every 3 along, we're going... Sorry, for every 3 up, we're going 1 along. So the same here. If we look at the fraction, at the top, it's when we're talking about a gradient, y is the change in x, which is for every 3 along in x, we go down by 1. So actually, if we go down by 1 and 3 along, we got our next point. Okay, we could also go backwards to find the other point, so go 3 along that way and up 1 just to get that next one. Okay, so again, the change in y is minus 1, the change in x is 3, hence a gradient of minus a third. So if we do down by 1 and across by 3, we get our next point. And then as before, we're going to join that up with a line as best we can. That's terrible. Let's try again from here. Right, as you can see, my line is never quite 100% accurate. Like if we really zoom in, you can see I've only just missed the mark. But again, you're not going to be penalised for being slightly off, in case anybody was worrying about that sort of thing. And I know somebody will be. Right, okay. What's the gradient of y-intercept? What's the gradient and y-intercept of a line when it's just an equation? Well, by now we should have spotted a pattern that actually most line equations are generally drawn in the form y equals mx plus c, where the number in front of x is the gradient and the number on its own is the yi. Okay, so following that rule, the gradient here must be 4 and the yi, be careful here, must be minus 5. Okay, right, this one's obviously done to trick you. The gradient this time is minus 7, okay, because it's the number with the x, and the yi is 5. Right, now this one, we can't just read this off straight away because it's not in proper y equals mx plus c format. You can't read the gradient off until the equation is kind of lined up neatly like that. But we can fix the problem easily by dividing everything through by 3. Why did we divide everything through by 3? Well, remember, we want y to just be 1y or just on its own. So we divide by 3 and that fixes that. We end up with 1y equals 3x plus 5 over 3. And it's a shame that's a fraction, but that's life. So our gradient is 3. Our yi is 5 over 3. Something I've forgotten to mention here, if you put a gradient of 4x, I will mark that as incorrect. That's not what we're talking about when we're talking about a gradient. A gradient is just a matter of steepness, which is a number. Okay, timesing a number by 4 is what gives it its steepness of 4. Okay, x is sort of a mystery number that's kind of changing as you go along the line, but it's not the gradient. Right, in this occasion, we've got equations. You've got to figure out the equation just from looking at the line. Okay, so first of all, easiest bit as always, the y-intercept. Okay, the y-intercept is 3. Guys, by the way, the most common thing I see students, especially year 8 students, do is to get the y-intercept and the gradient mixed up. Okay, so just if I'm thinking about anything, like to make sure you're 100% on before you go into Monday's little marked work, don't get the yi and the gradient mixed up. So the yi is 3. So whatever our equation is, it's going to be something x plus 3. Okay, so the mistake I see people make is to put the gradient there. But you're not going to make that mistake, I hope, especially as I've mentioned it. Right, I can pick any 2 points. I'm just, to prove a point, going to put my point here. Okay, so change in y is 2, change in x is 2, 2 over 2 is 1. And of course the gradient was 1. Yeah, for every 1 along, 1 up, of course it was. So our gradient's 1x plus 3. We don't really put 1s when they're with anything in maths, do we? You know why. I always make my pink elephant example. Well, no, it's not the pink elephant example. I always use myself as an example, don't I? You don't talk about one person entering into the room, we just say a person has entered the room. Right, for this equation here, the yi is minus 3. Okay, the gradient is 2. Okay, so y equals 2x minus 3. I've rushed through that one a little bit more because hopefully you're more comfortable with that one now. But again, make sure you get the y-intercept and the gradient the right way around. Really common mistake is to get them the wrong way around. So the most common error I see here is people writing minus 3x plus 2, and it's very frustrating for me to see because they've done the hard work and then dropped the marks. So hopefully me scribbling that out hopefully scribbles that out of your memory. Right, this is this very strange one where technically there's no gradient. Okay, and the y-intercept is 4, so it's y equals 0x plus 4. This is the pink elephant example. If if you're hanging out with 0 pink elephants, well, you don't mention it. Otherwise, people would think you're, losing the plot a little bit. So we just write it as y equals 4. I haven't done this example here, but I might as well. When the line goes vertically, we call it x equals minus 2. The actual gradient conversation breaks down here because this has got an infinite gradient. Infinity doesn't really occur in mathematics, or it does, but once you deal with infinity, we start to have all sorts of strange unexplained things happen. So for now, stop worrying about the gradient. We actually call it the x equals minus 2 line because every coordinate on that line has an x coordinate of minus 2. The y coordinates are changing, but anything on that line, remember, the lines are just a rule, and if you follow the rule, the line is drawn. That's why mathematical equations can actually describe motion. Is that if you follow a mathematical rule, you can actually create lines in all sorts of particular directions. Anyway, I digress. Right, this last one here, I've got a yi of 3. I've got a gradient, be careful, of minus 3. So my equation is y equals minus 3x plus 3. Right, almost there. Right, you also have to be able to draw a graph from an equation. So drawing the graph of y equals 3x minus 2, y-intercept minus 2, gradient of 3. Hopefully we get quite fast at these by now. I'm losing the will to do the proper lines. There you go, looks like that. Done. Right, minus 3/4 x plus 2. Ooh, a gradient like that becomes difficult until you remember that we can set it out as a change in y over change in x. So the change in y is minus 3, the change in x is 4. That's how we ended up with a gradient of minus 3/4. So going from the y-intercept of 2, I'm going to go along by 4 and down by 3. I remember I'd mucked this up before because if I go down 3 and along 4, unfortunately it got off the edge of the graph, but pretend I drew my graph paper properly. Don't worry, in the real thing it will be, and I go through there. Almost there. Right, so this is a real life graph and you just have to be able to actually interpret it. Remember I said that these can be quite abstract at times, but ultimately we do use these graphs to describe real physical processes going on in real life. So for this graph here, this is representing, let's say, a spring with weight being added on. Okay, so the y-intercept is 8. Okay, we haven't got our 4 quadrants like normal, but all the rules work exactly the same. What does that represent in real life terms? Well, when there's 0 mass added, there's a length of 8. So that's what it means. When there's no mass added to the string, then a spring. When there's no mass added to the spring, it's 8 centimeters. You could also say it's quicker to say the spring's resting length is 8 centimeters. Right, our gradient, be careful because sometimes the squares don't actually always represent the change, because the scale might not always be 1 square per number. It does happen to be in this case, but not always with real life graphs, and I'll see what mood I'm feeling in, whether I decide to give you the nicer version of the real life graph or not. Right, so there's a nice coordinate we can use. I don't see any other nice ones nearby. Oh, okay, well, I guess, oh, there we go. One there. Right, okay, so that's a change of 2, and 1, 2, 3, 4, 5. Change of 5. So the gradient is 2/5. Okay, or 0.4. Okay, what does that mean in real life terms? Well, if there's a steepness of 0.4, it means for every 1 gram of mass we add along, we add 0.4 centimeters to the length of the spring. I'm not going to write it all out, but I'll just say it. What it means is that for every 1 gram we add, we go up by 0.4 centimeters in length. Right, we sometimes have to draw graphs where they're not written in nice y equals mx plus c format. There is actually an option you can rearrange, but that's not actually the easiest way to do things. So the easiest way to do these things is to actually pick a coordinate where x is 0. Okay, when x is 0, then 3x plus 5y equals 15. Well, if x is 0, then 3 times x is nothing. So when x is 0, we can now figure out what y's got to be by solving it as a basic equation to make this work. So if x is 0, and we've got 5y equals 15, then when x is 0, y has to equal 3 to make that work. Okay, then we pick a coordinate where y is 0. Okay, and we do this equation solving again, but obviously if we know that the y coordinate's 0, then 5y is worth nothing. So when the y coordinate's 0, we've just got 3x equals 15. So we solve that equation by dividing both sides by 3. So we get x equals 5 on this occasion, because 15 divided by 3 is 5. So we now get 2 coordinates we know are on that line graph. 0 across 3 up, which is here, and 5 along 0 up, which is here. Okay, so that graph actually looks like, I was hoping to do a straight line there. Let's try again. So that graph actually looks like so. Right, for the next graph, I've given the same numbers, by the way. So for this one, we've got y equals minus 3x plus 5y. So when we've got minus 3x plus 5y equals 15, and we make x 0, then we end up with, well, we end up with y equaling 3 again. Okay, but when we've got minus 3x plus 5y equals 15, and we make y 0, then actually we've got negative 3x equals 15, so we have to divide by minus 3 to solve that. Okay, we're always dividing by whatever coefficient's left behind, so we get minus 5 as our answer there. So our coordinate's going to be 0, 3 again, but then minus 5, 0. Okay, so this line actually looks like so. Okay. Right, for this one, I think we've got a bit of space down here. We'll do this. So if we make x 0, then that means we cross out that, and we end up with minus 5y equals 15. Okay, so when we divide both sides by minus 5 to solve that, we end up with y equals minus 5. Yeah, 15 divided... No, we don't. 15 divided by minus 5 is minus 3. Okay, if we do that same one again, minus 3x minus 5y equals 15, and this time we fix y at 0. Then when we solve minus 3x equals 15, I'm not going to do the full thing anymore. We get minus 5, 0. So our 2 coordinates are 0, minus 3, which is here, and minus 50, which is here. Hopefully you're starting to see a nice little pattern appear. The final one, I'm not going to go through the whole thing. I'm running out of energy at this point, but we end up with like that. There you go. Who says maths isn't beautiful? What a nice little pattern we've got there by adding 4 line equations together. Right, I was going to throw in gradients as well from 2 points. So remember the rule I told you is take one of them and put it above the other in a subtraction, because you're looking for the change in y and the change in x. So if we take 10, 5 and 3, 19 and we subtract them between each other, because remember subtraction helps us find the difference between any two numbers. So between 10, 5 and 5, 19, the difference in x is 7. 10 minus 3 is 7. Now, when we do 5 minus 19, we get minus 14. Okay, so that's our change in y, that's our change in x. So minus 14 over 7 gives us minus 2. So that's the gradient of a line between those 2 points. Okay, right, minus 3, 5 and minus 6, minus 4. It doesn't actually matter what order you put them in. Putting negatives in makes the whole thing a little bit more difficult. I'll show you why now. So when we do our subtracting, we haven't got a problem here. Minus 4 minus 5 is minus 9. Minus 4, you take away 5, you go down to minus 9. Here we get a double negative. Minus 6 minus minus 3. So minus 6 minus minus 3 becomes plus 3. So we're actually doing minus 6 plus 3, which gives me minus 3. Okay. And when we do our change in y, divide by change in x, minus 9 divided by minus 3, we actually get a gradient of positive 3. So actually, despite all the negatives we've got there, the gradient between those 2 points is positive. You might think, well, hang on, what's going on there? Let's actually sort of do a rough idea of where those coordinates are. Minus 3, 5 is like, well, it's across to the left and up here somewhere. Minus 6, minus 4 is... I've drawn the wrong graph for this, let's try again. Minus 3, 5 is sort of somewhere up here. Okay, it's across to the left but up. Minus 6, minus 4 is across to the left and down somewhere. So the 2 points are like that. So if I actually join the two together, that's a positive gradient graph, isn't it? Yes, that's a negative coordinate, but if you go backwards, it's even more negative. So clearly going to the left goes down, going to the right goes up, and it's positive gradient. But again, if it's confusing you, just follow the maths. It always sorts it out in the end. Right, percentages and proportion. So the first thing it's key to understand is how to go from a percentage to a decimal. Okay, so 34%. It's important to know what the percent button actually means, symbol actually means. Percent actually just mathematically means divide by 100. Per 100 out of 100. Divide by 100. So when I say 34%, I actually mean 34 divided by 100, which can be achieved by just moving the decimal point to make it 0.34. Okay, so 34.0% essentially becomes 0.34. So you just move the decimal point twice from the invisible end where it starts, and you got the decimal version of it. Okay, why do we need it as a decimal? Well, for calculations we're going to do later. Okay, so what's 237% as a decimal? So just check, that is 2.37. Okay, just check you don't think that we just put the point in front of the first number. No, we're moving it twice from the end. Okay, now how can something be 237%? Surely 100% is the maximum. Well, no, things can grow double their size, or more than double their size, so therefore we can actually have more than 100% when we're talking about growth, for instance. There are examples as well, but that's just one example. Okay, so this is how we use this. Once we know 38% is 0.38, if you're asked to find 38% of 34, this is a unit where your calculator can do all of the heavy lifting for you. 0.38 times 34 is all I have to do. Okay, I'll just type that into my calculator, which is 12.92. Now just be aware we are talking about money in this particular question, so I want to leave that as £12.92. Okay, 156% of 745. That means we're doing 1.56 times 745. Okay, so 1.56 times 745 is going to give me 1,162.2. Right, 236% of 540. I know what I was thinking here, but we don't actually need that question. Let's move on. Bless me. Right, what happens when we increase 40 by 24%? Okay, so 40 is what we originally start with, and we've added 24% on. Okay, now a common mistake to make here is to times by 0.24. Okay, well that's not going to work because that's going to leave us with a number much smaller than 40. What we need to remember is that every number starts as 100% of itself. Okay, so if we've increased 40 by 24%, that means we've started with 100% and we've now got 124%. So we need to do times by 1.24 to get our answer. Okay, and you will know when you've probably done it right because you'll get a number that's bigger than what you started with. Let's do that there so that looks a bit nicer. There we go. So 100% of the number is 40, 124% of the number is 49.6. Right, we're decreasing. It's the same concept. We start with 100% of the number we had, and we're minusing 34%. That means we're going to only have, we're only going to have 66% of the original number left. Yeah, we had 100% when we started, we lose 34%, so we've got 66% of the number left. So we actually need to times by 0.66 to get our answer, which in this case is 39.6. Okay, that's how we increase and decrease by a number. Right, reverse percentages. Key skill. The reason I said it's a key skill, this is something they're asking the GCSE more than any other percentages question, and it's a question that people make mistakes on more often than any other question. So you need to be really careful when you approach one of these questions. And here's why. So we take a number and it gains 34% and it's now 6,700. Okay, so the temptation here with a question like this is to say, okay, 6,700 times by add 34%, so that's going to be 134%. So I need to times by 1.34, and that'll be my answer. No. Look at the language here. You're being asked to find out how much you originally have, and we now have 6,700. So you've been given the answer to the question, and you've got to find out what the original question started with. Okay? So we added on 34%. And this number we're going to call x because we don't know what it is. Well, we know it was 100% of itself, right? Every number starts with 100%. It was originally 100% of itself, then we added on 34%. So we've now got 134% of the number. That means we had to times our original number by 1.34 to get 6,700. Okay? So how do I reverse that? I need to divide my number by 1.34. Okay, so if I took my original number and I times it by 1.34, I get 6,700. Therefore, mathematically, if I take 6,700 and divide it by 1.34, I'm going to get my original answer, which is 5,000. And you know when you've done these right, because about 80% of the time, and not all of the time, but 80% of the time, you get an answer that looks a lot more nice and well-rounded than what you originally started with. Okay, and you can test it the other way around. If I do 5,000 times 1.34, if I add 34% to 5,000, I get 6,700. Of course I do, because I'm right. I always am, apart from when I'm not. Right, so this is reverse percentages, but watch out, this is a discount. It's a reduction. So we've started with a certain amount, and we've lost 15%. And now we've got £297.50. Okay, I'm feeling glamorous this afternoon because that is an expensive pair of shoes that we're selling here. But I know shoes can cost that much, so I will go with it. So £297.50. Remember that if we've reduced it by 15%, then what we've got is 85% of the original price. Now look, we use the word before here. They're not always going to use the word original. Look for things like original, before, and the reverse percentages. They're asking you to find the thing that came sooner in time, which originals do and befores do. So look for that past tense language. Okay, so we had to times by 0.85 to get there, which means if we want to reverse, we need to divide by 0.85. If we take our original amount, times it by 0.85, then we get £297.50. Therefore, if we take £297.50 and divide by 0.85, we'll get our original amount, which in this case is £350. And again, look how much nicer that looks than that. Okay, so for your sort of one to have a go on your own, I've given you two reverses. One's an increase, one's reversing a decrease. You've got to figure out which one is which. There's two questions here. I'll pause the video while you have a go. No, well, I won't pause the video. You pause the video to have a go. Okay. So, this one here is actually reversing a reduction. Reduce, obviously. So, our house costs... by the way, sorry. You'll notice here, by the way, they didn't use before or originally, but they gave you time values. If they're looking for the cost in 2016, that's past tense, isn't it? If it's now 2017, 2016 was before. So that's another way they can tell you it's a reverse percentages question. Okay, so this house reduced in value. Okay, so yeah, we had to take off 5%. Okay, so we had to times by 0.95 to get 323,300. No, wait, 323,000. Okay, so I need to divide by 0.95. Okay, 323 divided by 0.95. Sorry, 323,000 divided by 0.95 gets me £340,000. Again, much nicer, more rounded number than what we originally have. Alright, a man eats a larger dinner and increases his weight by 14%. Okay, that is quite ridiculous. That would we'll get to how ridiculous that is in a minute. Yeah. So he originally weighed a certain amount before increasing by 14%, meaning he's now 114% of what he was, which takes him to 102.6 kilograms. Okay, so we must have had to times by 1.14 to get him up to his new weight. Okay, so it follows that if we want to reverse that, we need to divide by 1.14. You are always reversing with a you're always dividing with a reverse percentages question. So 102.6 divided by 1.14, we get 90. Again, 90 kilograms. Nice rounded number. So that's like 12 kilograms of food, which is roughly 25 pounds worth of food. Yeah, that's a lot. I think the world record for like most amount of food ever eaten is 10 pounds. So you're certainly very hungry that meal. Right, person's paid £30,000 a year. Sorry, next skill. Persons paid £30,000 a year. After a pay rise, they are now paid £34,000. How much has their pay increased by as a percentage? So this is percentage change. I probably should have put a title in here. So it's calculating percentage change. And there's a simple formula for it. Change over original. Okay. So you're looking for what was the original amount. Well, they were paid 30, they're now paid 34,000, so the thing that came first in time is 30, so they originally were on 30,000 a year. How much has it changed by? We could just look at that, can't we? The difference between 30,000 and 34,000 is clearly 4,000. Be careful not to lose a zero anywhere on that. And then just type that fraction into your calculator. Yeah, let your calculator do all the work here. And it gives me, well, it gives me just a fraction simplified back, which is 2 over 15. But if you press the ST button, it will give you 0.13333 forever, which is 0.13 recurring. Just round this to 2 decimal places. So 0.13, that's absolutely fine. So that's 13%, okay? Presumably you know how to go from decimals back to percentages. You just move that decimal point twice the other way. Okay, right. So, this one here, 120 pupils in year 8, but 103 pupils in year 7. What percentage less pupils are there in year 7 than year 8? Okay, so I've put this one in because the change is obvious, right? The change between them, the difference between 120 and 103 is 17 pupils. But what counts as the original? What percentage less pupils are there in year 7 than year 8? Is 120 the original or 103? You know, if in doubt, I would go with the number that comes first in the sentence. But because they're saying how much less is year 7 than year 8, year 8 is what we're sort of comparing the reduction to. Okay, so in this case, the year 8 is the original, so it is 120 in this case. So 17 over 120, if we type that into our calculator and SD it, hang on, my calculator's having a funny moment, then we get 0.1416 forever. Okay, so I'm going to round that to 0.14, which is 14%. Right, this is often then used to give you a profit question. So a business buys 4 books worth of books and sells them for £5.50. What percent profit have they made? Okay, so we can clearly see the change is 150. The original amount, well, they originally spent £400. So it's 150 over 400. And again, just type. You don't even have to use the fraction button in your calculator. You can just do 150 divided by 400 and you'll get the same result. I get 0.375. I'm actually not going to round that because it's a terminating decimal. It doesn't go on forever, so I'll keep it like that, which means my answer is 37.5%. If there's a particular amount you need to round to, you will be told. Right, direct proportion. This is a nice to know for now. So don't worry too much about it. We're generally going to deal with using ratios here. Direct proportion, as one variable increases, so does the other. So if someone's paid £30 an hour, pay in hours are directly proportional. And we can actually make a formula for it. If you take 30, times it by the amount of hours, you'll get the pay. Okay, so multiplying hours worked by 30 will give you your pay. We can represent this as a ratio the opposite way around. You take your hours, you times it by 30, you get your pay. Okay? On a graph, it would look like this. Again, it's a nice to know for now. Don't worry about it too much this term. Right, inverse proportion. That's supposed to say inverse. It can sometimes be described as indirect, I think, but inverse more commonly. Inverse proportion, as one variable increases, the other will decrease. So a common one is sort of work and time. If people are working on a building, if people are working on building a house, if people are working on building a house, the more people working, the less time it will take to build. So people and time is inversely related. We can still relate this to ratios, but we'll come to that later. Okay, so it takes 400 grams of flour to make 25 cakes. So we can write this as a ratio. 25 to 400. Okay. Right, now there is two ways of doing this. I'm going to do my way for now. But you may have had your teacher teach this to you slightly different. So apologies for any confusion. Right, so we write this down as a ratio. 25 cakes requires 400 grams of flour. We need 35 cakes. So it's like, how do we get from 25 to 35? Well, our reliable route is to go via 1. We all know how to get from 25 to 1, and we all know how to get from 1 to 35. To get from 25 to 1, we need to divide by 25. To get from 1 to 35, we need to times by 35. You can actually, by the way, convert that into 35 over 25, like one single mathematical function, but don't worry about that too much if that confuses you. So, to get from 25 to 1, we divide by 25. To get from 1 to 35, we times by 35. Okay? So again, those of you that have worked this out, you can actually times by 35 over 25 to get your answer. But again, ignore that if that doesn't really make sense to you. Okay, so what we need to do with ratios is whatever we do to one side, we must do to the other, like equations. So if we divided 25 by 25 to get to 1, we have to divide 400 by 25 to keep that equivalence. Okay, so 400 divided by 25, I've got no clue, I think it's 16. It is 16. Okay, and then if we need to do times by 35 to get from 1 cake to 35, then we need to times by 35 to get from 16 grams to how many grams is required for 35. Yeah, we've got to do the same thing both sides. So if I do 16 times 25, times 35, I get 560 grams. You know you've done it right because it will look about right. Yeah, it's 35 is about a third more. 560 is about a third more than a 400. That seems to make sense. There are many, many ways to do this. I could be here all day doing this, but I don't want to be here all day. So this is just the one technique I'll show for now. Right, you can have this question asked in a reverse way. So we know that 25 cakes makes 400 grams. 25 cakes requires 400 grams. We could actually be asked, okay, well, how many cakes were 500 grams? Okay, before we had cakes, so we had the amount of flour as the missing element. Now we've got the amount of cakes as the missing element. Okay, this was missing before. Now it's this that's missing. Okay, but the method's the same. We take the root via 1, because that's easy to do. To get from 400 to 1, we divide by 400. To get from 1 to 500, we times by 500. Okay, those looking for shortcuts now know the multipliers, 500 over 400, or 5 over 4. But to those who don't know what I'm talking about, ignore that. Right, okay, so we do the same on the other side. We need to divide 25 by 400. And I know that may seem a bit uncomfortable, but we're basically saying how many cakes can you make with 1 gram of flour? Well, obviously, not very many. In fact, our answer is 0.0625 cakes, so we couldn't even make a tenth of a cake. Okay, but if we follow the next part of this, which is to times by 500, we get something that seems a little bit more familiar to us. 31.25. Okay, so 500 grams of flour makes 31.25 cakes. Now we've got a problem here. You can't make 31.25 cakes. So what's the answer to this question? Well, I'll accept both. Realistically speaking, since you can't make partial cakes, we can make 31 cakes. And I'll accept that as an answer. But I'm also sort of more than happy to accept you can make 31.25 cakes. So you can make 31 cakes and a bit of a cake. It's fine. It doesn't, that's fine. Okay, either of these would be accepted in the exam. I can see why some people would round. I'm happy to keep it as a decimal. Right, this is an inverse. No, it isn't. This isn't an inverse. This is a question I've made for you guys to practice. Okay, so I'll pause the video whilst you guys have a go. No way, I'm not pausing the video. You're pausing the video. Okay, so 5 pizzas feed 12 pupils. I don't know how generous you feel that is, and I'm aware that obviously it depends on how hungry the pupil is, how much they like pizza, but we just assume they're all eating an equal amount of pizza. Okay, so we need to know how many pizzas will be required for 20 pupils. Pizzas. Pupils. Okay, right, so we take the root via 1, which is easy to do. We need to divide by 12 times by 20. So we do the same this side. 5 divided by 12. Okay, so we get 0.416666 forever. Right, so in this case, I would actually use the ants button in my calculator. I store whatever the answer is to get more accuracy and times that by 20. Okay, so 20 times 0.4, sorry, for you put 20 times 0.20 times ants, we get 8.3 recurring. So we need 8 pizzas and a third of a pizza. Again, I'm happy to accept if people have put 9 as their answer to that one, because you say, well, you're not going to be cooking a third of a pizza, and 8 pizzas isn't going to feed everyone, so you need 9. And I'm sure somebody can hoover up the extra slices, but I'll accept either. Okay, right. Now I'm aware of a slight typo I've made in the next slide. I am not suggesting cannibalism. How many pupils can we feed with 6 pupils? I don't know how many pupils a pupil can eat. But what I meant to say is how many pupils can we feed with 6 pizzas. Please do not eat your fellow students. They have a lot of learning to do. Right, so we've got 5 pizzas to 12 pupils. And we want to know how many pupils we can feed with 6 pizzas. So again, we take the known root via 1. If we divide by 5, we'll work out how many pupils we can feed with 1 pizza, and then times by 6, we'll work out how many we can feed with 6. I'm aware that you may have been confused by this question at this point. I may not have done it, but in case you have. So 12 divided by 5, 2.4. Okay, and 2.4 times 6, 14.4. Okay, so again, I'm aware that some of you may want to say, well, that's actually only 14 pupils. If we've not fully fed the 15th pupil, then it's only 14. But I will accept that 6 pizzas, not pupils, will feed 14 pupils or 14.4. Happy for you to keep it decimal. Okay, right, this is an example of inverse proportion. So we can write this as a ratio still. 5 people take 20 days to build the house. But since it's inverse proportion, whatever we do to one side, you have to do the opposite. You know that as one increases, the other decreases, and as the other decreases, the other one increases, and it's proportional. So we do the thing we did before. We go, right, so how long would it take one person? So if we actually divide by 5, times by 7, we get that bit. We know how we get from 5 to 7. Okay, so we have to do the opposite on the other side. So if we divided by 5, we times by 5 on this side. Okay, so that gives us 100. Again, operationally, that should make sense, right? If it takes 5 of you 20 days, if there's only one of you, it's going to take 5 times as long to finish that house. Okay, and then if we needed to times by 7 on that side, we need to divide by 7 on this side. Okay, again, we don't always get satisfying answers here because we've got 14.285, which I'm going to round to 14.3. Okay, I would suggest leaving that as your answer. You can have 14.3 days. If days isn't a discrete value, you can have a bit of a day. So it's 14 and a bit days, 14.3 days. Check if it makes sense. If you've got 5 people and it takes you 20 days, then when you've got 7 people, it should take you less time. So you're looking for an answer less than 20. So 14.3 makes sense. Right, so here's a question for you to have a go at. Okay, so 10 people take 15 days to paint the fence. How many days can 4 people, not fence, house, paint the house in? So again, people to 10 people to 1 people to 4 people, divide by 10, times by 4, and we do the opposite on the other side. So if we divided by 10 on the other side, we times by 10 on this side, which gives me 150. Okay, if it takes 10 people 15 days, then only one person's going to take 10 times as much time, 150 days. So that poor person would be there for half a year, so they need help, don't they? So again, if we times by 4 on that side, we divide by 4 on this side, which gives me 37.5 days. Still quite a long time, but you know, a month doable. Remember, days we can leave as a decimal there. Yeah, and that's the end of Unit 5, Percentages and Proportion.